So once again, good evening, one and all, and welcome to our call this evening. We're really happy to have a very special call this evening with the help of one of our sponsors, and that's Altair, which is based in Detroit, Michigan. And we have for you here Erik Larson, who is one of the representatives of Altair as the Senior Manager of Global Academic Training. So clearly, Erik will have a lot of really great content and information for you this evening about Altair's product, particularly having to do with CAD. And I'm going to turn it over to Erik, who will introduce our CAD topic and how you can build better robots faster with the Altair software suite. So we will offer a warm welcome to Erik Larson. Thank you very much for joining us this evening.
Thank you so much. I really appreciate it. I appreciate the opportunity to speak this evening. And we're going to, as mentioned, we're going to talk about, I believe the formal topic is going beyond CAD, building better robots faster. So we're going to talk tonight about once you have your robot or your individual parts in CAD, where can we go from there? Where can we improve our designs utilizing analysis softwares? And I'm going to try sharing here. Hopefully that will work. And share. So hopefully you are seeing my screen now. Is it showing up?
Yes.
Okay, perfect. Okay, so let me just minimize this Teams window here, and let me start with here. So unfortunately, my camera is not working right now. Bit of a technical issue. So I went and last week, I was at a competition down in Kentucky, a solar car competition, and they snapped a picture of the ceremonies when we passed out a big check. So that's me a week ago. So at least you can imagine what I'm looking or what I look like as I present here. And as we discussed, we're going to talk about a software of ours called Inspire and going beyond CAD to build better robots faster. So you have CAD'd up your parts. You're beginning to prepare your robot, and that's fantastic. And CAD is absolutely vital to building better robots. But what we'd like to discuss is once you have that CAD geometry, other things that we can do with it. In particular, things like analysis. So investigating linear, static, normal modes, understanding the behavior of that geometry, understanding how it's going to behave when we accelerate the robot or turn the robot or inadvertently smash into another robot, or what sort of stresses are going to happen, what's going to happen when I raise my arm to shoot that note into the scoring. Better understand our robots so that we can make sure that the parts that we design in CAD and ultimately manufacture and put onto our robots are of sufficient strength that they're not going to bend, that they're not going to deform, or worst of all, that they're not going to break. And in fact, this is an example of a situation where a team had run an analysis on one of their parts, and it showed that it had a high stress level here and was likely to break there. And sure enough, that's exactly where the part broke. Another thing that we can do with our CAD geometry, and a little bit more advanced beyond analysis, is what we call optimization. And the idea behind optimization is to make our parts as light as possible. Every extra ounce, every extra pound that we're moving around the field slows us down a little bit, takes a little bit more of our battery power, makes it so our shooting arms go up a little more, makes it so that when we have to hang on a chain or a bar or climb something at the end of the competition, our motors, our actuators have to work a little bit harder. So we can take our CAD geometry and utilize a software like this to make it as light as possible while being aware of the strength requirement of those parts, and make sure that our parts are the least amount of material, but as strong as we need them to be. And then finally, the other thing that we can do is motion simulation. So there's a ton of moving parts on your robot, and we are CADing them up, we're getting them all set and imagining and kind of theorizing how they're going to work. With a software like Inspire, we can take those CAD geometries, we can simulate the connections and the joints between them, and then actually see them move and understand how they're going to behave and make sure we don't have interferences, or find out if I'm going to raise that arm to shoot, make sure it raises properly to the proper height, and find out how much work is required to do that. What sort of motor or what sort of actuator is going to be necessary to do that. All of these things can be done in a software like Inspire. Most importantly, software or Inspire works with all CAD geometries. And I'm going to go through a quick few slides here, but then I'll actually demonstrate it utilizing the software. It can use any software or any CAD format that you have. No matter the CAD system that you're using, whether it's SolidWorks, Onshape, ProE, CATIA, whatever CAD system you're using, we can bring in a file from it, bring it into Inspire, and begin to work with it. We have a broad material library so that whatever material you plan on making your robot parts out of, we can very accurately simulate them. We have a broad library that contains many, many commonly used materials, or we can add our own materials so that we can guarantee that the weights we're measuring, the stresses that we're analyzing, the motion that we're analyzing, it's all correct and accurate to whatever we're building our robot out of. We can very simply, once we bring that CAD geometry in, we can very simply and accurately represent how that part is being held onto our robot, and then very easily add a loading to it, indicate where a force on that part is going to come from, and be able to accurately understand how that part is going to behave. So this is the torsional analysis on a robot frame, and setting it up for an analysis is very simple. In fact, can be done literally within minutes after bringing the CAD geometry in. Then we can choose the type of solutions that we want to analyze, and we can do it very quickly. We have two solvers, two analytical engines that can do both optimization and very, very, very rapid analysis. In fact, this part right here, it's an assembly of 41 individual parts, and it took 5 seconds to analyze. So from the CAD, from opening this, you generate the CAD in your CAD software, from opening it up in Inspire to creating the loads and the supports on it to actually running it, I had answers in 2 minutes. So very quickly, very easily, and very simply, we can get a very accurate answer as to whether we have designed our parts sufficiently for what we want them to do. Optimization is taking heavyweight parts and assigning only the material that's necessary, determining how forces are going to go through a part so that we can guarantee that we have the lightest weight part possible, but yet strong enough to meet whatever requirements we have for it. Motion analysis allows us to see the behavior of our robot very easily, very quickly. We can bring in the geometry to find the relationships between all of the different geometric entities in it, and determine how it's going to move. Make sure that it's moving the way we want, and then even do things as you're seeing here. Grab a graph off one of the motors to understand how much torque is required to achieve our goals. And with the accurate material representation, it's a very accurate representation of the amount of work we're going to expect that motor to do. So we can validate whether a motor that we already have will work, or use it to determine what sort of motor we need to acquire for this. And we can even then couple the motion simulation with analysis. So you're seeing a dynamic simulation here. This is telling us the stresses on this part as this intake arm goes through its entire range of motion. So we get a very accurate understanding of how the stresses are going to happen on this part. So we can, while it may be perfectly fine in one orientation, once we lift that arm up, it may not work. And so we can make sure that we design our parts for all possible scenarios. And we can even use that information then to optimize a part and come up with a part that's as lightweight as possible, but meets all the requirements of the entire motion analysis. A couple of use case examples. I actually am going to cover these after we go through a demonstration. But use case examples of teams that are out there that are actually utilizing this right now. The hot team, the goon squad team, a number of other, and we've got a whole bunch of, I'm sorry, this is the Bearcat Robotics. The goon squads have used it. A number of local Michigan teams and teams around the country that have utilized this software. And we'll talk about a little bit more about the use cases afterwards. I really would like to get directly into the software. What I'd like to do though here before I start showing you examples live in the software, are there any questions that anybody has about just kind of this quick PowerPoint presentation or clarifications before I actually get into demonstrating it? I'd be happy to address anything. Looks like someone popped up and unmuted themselves. Arjun, and I see William, you got a question. I'll get to you. Arjun, did you have a question?
Yeah, I'm actually curious. Can you work with, for the topology optimization, can you work with non-isotropic materials? So say you have something you want to 3D print, can you specify which way the layer lines are going? And can you specify things like infill and amount of walls that you're going through? Because that's something that we work with a lot as a team. It's like we print something, say it's what have we printed? Like I don't know, something functional. I can't think of one. We're mostly printing spacers, but we're always thinking, okay, how many walls should we use? How much infill should we use? What temperature should we print this at? I'm not sure if that advanced, but even things like walls and infill, and then optimizing topology based off that. Is that
So the
something
short answer is yes, that can be done. Unfortunately, the long answer is you're going to have to go to another one of our softwares, which is far more in depth than the Inspire software. It will take a fair amount of learning. It's called hypermesh, and it's traditional finite element analysis, where you're actually modeling elements, and you can model all of those different layers, thicknesses. As for heat, that might be a little bit of a challenge, but we could model up the different layers and have a non homogeneous material, but that does require a little bit more effort. For the software that we're showing, and what we really kind of promote to first, what you would need to do is get the material properties from that individual or from that specific layup that you've done, and then use that as the material properties.
Okay. Yeah, I was curious also because you have that print 3D tab there. I'm not sure if you can do analysis.
Yeah, so what Print 3D does is it's actually a printer simulation, but for SLS type printing. So what when you melt a powdered material with a laser and then it cools, it builds stresses into the part. So it's an analysis of the actual printing process, but it's strictly for metallic SLS right now, though I hear polymers are going to be coming sometime. So.
Yeah, like nylon SLS. Yeah, I've used some nylon SLS before, not for robotics, just for other things. But yeah,
excellent.
Okay.
Thanks.
Yeah, thank you.
Well, you bet, William. I see your hand up there. So
yeah, I just wanted to bring up the idea that this software is in the kit of parts. Is it not?
Thank you. Yes, I appreciate you bringing that up. Yes. Yeah, so it is in the kit of parts. And in fact, after I do some quick demonstrations with the software, I will show you where that kit of parts link leads you. It's our support for FIRST Robotics. Everything that you need to learn about the software. We've got some videos here. We even had had Dean Kamen participate in one of our webinars, and it's a great interview with Dean Kamen. Getting the software, learning the software, RapidMiner, where you can get student editions and sponsorships, and also some previous webinars that we've done. So tons of information in here, and we'll talk a little bit more about it. But yes, we are in the kit of parts, and it will lead you directly here where you can download Inspire, and it's a quick and easy download. Very simple to do. So William, thank you. I appreciate you pointing that out. Okay, so let's start here. So this, in fact, let me just open this up. If I come here, this is a step file, and if I grab that, it will open up that step file and bring it immediately into Inspire. And from here, you can see this is 41 different parts. It will automatically bond them together, so it will behave as one individual part. If I want to do structural analyses, I can very easily come over here to structure. Supports are what hold something in place. So if I assume that I'm mounting this on these little holes right here, when I select those, it will hold those holes in place. So essentially simulating my bolting through those holes. And I'm going to go through things relatively fast here. This is definitely not meant to be a training session, but more just of a demonstration of the capabilities. On that website, there's a ton of material. In fact, utilizing all these models that I'm going to show you to show you how to do what I'm doing. Then if I want to add a force to this, I can say, okay, there's a force on this hole right here, and I can say it's 50 pounds force. And then I can come over to this hole right here and say that there's a 50-pound force on that hole right there. And then set this up for an analysis. Pick the solver that I want to use and run the analysis. And I'll click run, and it will very, very quickly run an analysis, and I will get results from this. This actually will take a little bit longer than the 5 seconds. Took about 10 because I've got a whole bunch of other things open. But now I can see my results. I can see how the part behaves. This is an exaggerated view. This isn't 1-to-1 scale, but I can see how it's going to deform as a result of those. But very quickly from CAD to analysis results, and I can understand the behavior of my part. Other things that I can do, this is that bracket. So this is analyzing a force on this part right here, allowed to rotate around here, but held solid in this location. And we can easily see where our potential danger zones might be, where there's a possibility that we may break this part. And as you saw in that example, and I'll show it to you again, that's exactly where the part broke. And they knew it was going to break, and utilizing the software, they had a replacement ready as soon as it did break. Moving on to optimization, we can take our big bulky parts, optimize them. This is what the hot team did. You can kind of see how that bracket once existed in there. So this bracket right here, you can see this hole, this hole, this hole. And it became this to this to this. They filled in all of this material, put those loads on there, and the solver told them where the material needs to be to handle these loads. And while this optimization didn't lightweight it, it actually kept it almost exactly the same. It provided them a better distribution, so they kept the weight exactly the same, but put material where it needed to be so that this part lasted throughout the entire rest of the season. But other things that we can do, and this actually is not a first example, but it's a great example. This is what I was working with the teams down at the Solar Car Challenge. They took this part right here, which weighs quite a bit in aluminum. It was almost 2 pounds. And utilizing the motion analysis, we're able to come up with a lightweight version of that. This is the part that you saw, but now a lightweighted version of that. that was an 86% reduction in mass, but yet still able to handle the forces that were put on it. So a prime example of lightweighting, of taking a heavy overbuilt part and reducing its mass to the point where it can still achieve the goals that you have, but do so with the least amount of material. And you can see, as we showed with this, it's very simple to create these scenarios, to bring the geometry in, to apply our loads and accurately apply our loads. Our loads can be, our supports can be applied to entire faces, to holes, to points, to lines. And then we can put forces onto there. We can put pressures onto there over an entire area. A torque, so something, we know that when we lock a motor down and it starts spinning, it's going to create a torque, so we can simulate the torques on there. Really any form of loading that you want, we can simulate and get accurate results as to how our robot and how our individual parts are going to behave. So let me pause there real quick. So we've kind of talked a little bit about analysis and optimization before we move on to things like motion and other things. Just any opportunity to ask any more questions if anyone has a question about what we've just discussed there.
Yeah, I guess it kind of in the interest of design for manufacturing. Well, a
Yep.
lot of our parts are laser cut flat sheet
Yep.
metal parts, and I know if you're milling a part, you'd probably want it to just be one side you can lay flat on the bed and go with a mill.
Yep.
Kind of with the solar car example, it looked like a very organic shape. But are there constraints you can set on the part before it optimizes it so that you can have, say, just like it's flat completely on one side, or it can't expand out in thickness?
I am thrilled that you asked that question because yes, that is a really good point. And in fact, this optimization was done with one of those constraints. So you can see this was the original part. They filled in all the area around the holes. And this, when we do an optimization, we create what we call a design space, which is essentially a big block of material that connects all of our loading and supporting areas, but doesn't go beyond it. So this entire process of optimization is subtractive. It won't add material, it will subtract. So you put all the material that it could possibly use, and then it will subtract from it. And if I just left it on its own, you'd end up with something like this solar car part, which is very organic. It's got holes going in multiple directions and may not be manufacturable by the way that you're looking to do. So if I'm looking to laser cut, when we do our optimization, we actually have these what we call manufacturing constraints. We've got draw. So this is used for metal forming or metal casting, where you have to have things pointed in a correct direction. But in the case of laser cut or water jet cut, we use a tool or a manufacturing constraint called extrusion. And it's represented by this blue square right here with the, looks like a little I-beam symbol there. And what extrusion does is, by defining this frame here, you've defined a normal, a direction of cutting, the direction your water or your laser is going to come in. So it will come in perpendicular to this plane, and what you then end up with is a part that looks like this. So it's a continual cross section all the way through. You can ignore kind of the bumpiness of it. That happens because of the underlying mesh.
Yeah.
But you can see how this would absolutely be able to be cut on a laser bed or on a water jet bed, because it's a constant cross section all the way through.
Yeah, that makes sense. And if you wanted more just like straight line segments and kind of more continuous curves, is there a way to smoothen these out in Altair? Or
Yeah, so
would you have to...
what you then do is you can do this and you click this fit polyNURBS button. I won't, because it'll probably take 3-5 minutes to run, but I'll show you what it ends up with, which is that right there. So it's a nice smooth geometry. You can actually manipulate these polynerbs and make it more square on the corners as opposed to the rounded edges. It tries to create the smoothest geometry possible. But you can also then bring this into your CAD system and manipulate it in there and flatten it out or do whatever you want in there. But this takes kind of all that internal bumpiness out of it and creates a nice smooth pattern from it.
Okay. Yeah, that's really cool. Yeah, that pretty much answers all my questions. Thank you.
Excellent. Oh, good. I'm glad. I appreciate all the questions. And the idea here is we want to get you from your design to your either analysis about whether your design is appropriate or a redesign through optimization, and then back to your CAD system and ultimately to your manufacturing process as quick as possible. And that's why we've catered these tools to do this, to be able to do something like double click on that part and click fit polynerbs, and 3 minutes later have a nice smooth part here that I can bring back into my CAD system, because we can save this as a step or a parasolid and go immediately back into my CAD system and pop this back onto my robot. Or I can ignore manufacturing constraints altogether and end up with a part like this that I would then have to 3D print in some way. So we can give you as much freedom as you want, or as many restrictions as you need to get the parts that you've designed. And when we take a look at some of the use cases, you're going to see a bunch of different variations of how teams used both the analysis and the optimization. So any other questions before I get into the motion aspect of things? Okay, then don't hesitate to stop me if you do have a question. So this right here, let me minimize that and come back to here. And why is it not? Oh, because I'm in here. There we go. And let's open module 5. Why is module 5 not opening? Okay, that's a little weird. That one's kind of frozen, so let me reopen that again. Give me just a second. Oh, because, okay, I know why it's not working. It's loading in the results. This was actually run in an earlier version of the software, and it's still loading in results. But we can see here, so this is a motion analysis. I can come here to my, this thing keeps getting in the way. Okay, there we go. I can come here to my motion and run an analysis here and see how that part is going to move. This is an old intake off of one of the team we work with, robots. And so we can see the behavior of that part through its entire motion. What I've done is I've defined the parameters for this actuator. And I can define actuators for linear motion, or I can define, did I download it? Let me see if I downloaded it here. Desktop, first presentation. No, I didn't. I'll have to get that. That's fine. This, let me come back to here. This right here, this is motors that are defining the motion behavior of this. And I can download module 4. Give me just a second here. And I'll open this. I thought I had this open. I apologize for the slight delay, but I can open this. And File Explorer. Why is it not? Downloads and 4 and motion. And now let's go to my desktop and first presentation. Let me drop that right in there. Okay. And there we go. Now I can grab this and motion analysis results, and we'll just pop this into here. And we can take a look at a direct motion analysis. Oh, darn it. It'd help if I cleared out what was there to begin with. So I apologize. I normally have this all set. I forgot to open up this one thing here. So this is just strictly analyzing the motion of this robot. This is not doing any analysis or optimization, but just understanding the behavior of it, how the parts are going to move relative to each other, how the motors are going to behave, how much force is necessary to move this robot around. A little slow to load up, but that's okay. Why is it taking so long? Okay, well, we'll move on from there and I'll come back to that. But then what we can do is couple that with our analysis and with our optimization so that as it begins to derive the data from this, as I come here and I can look at things like the forces that are occurring at all of my joints. So you see it's calculating all of the forces on this, and that then is being fed into an analysis on this. So I may not even know what sort of forces are going to be acting on my parts. The solver, the motion solver, will automatically calculate that for you and then utilize that to tell me how much stress, how much force is on this part. Is the part going to break? And you see these numbers are continually changing throughout the entire movement. So it may be safe in one location, but in another it's in danger. And this will tell me that. And then that can be used to drive optimization as well. This finally loaded up. So this right here is just geometry that's been brought in from my CAD system. Utilizing Inspire, what I do is I develop joints. I say, okay, this will rotate around that. This will rotate around that. This moves relative to this in this direction. And then I can stage the behavior of my motors. So I can say, okay, this motor runs first, this one second, this one third, and understand the behavior of my robot and make sure that I've got my angles correct, that I've got my links correct, that my robot is going to move in the way that I want it to. And then as was shown in the PowerPoint, I can grab information from this. So I now know that for this joint at this particular motor, for this motor at this particular motion, it's going to take 4 inch-pounds of torque. But then it's going to require 5.5 in the other direction. So I can make sure that my motors are sized correctly, or determine whether a motor I have is going to work or not, and understand the behavior of this and make sure that I have designed everything correctly. And in fact, I can even do things, I don't have the model here, but I've modeled up, and I believe we had a team model up, a robot lifting its arms and grabbing onto the chain and pulling itself up, and making sure that my actuators or my belts or whatever are going to be sufficiently strong enough to lift my robot up at the end of the competition. Basically, anything that involves motion, we can easily simulate within Inspire and understand better how our robot is going to work, whether the motors that we have are going to work, whether the parts that we've designed are strong enough to work, and then move on to make sure that the parts that are part of my motion assembly are as light as possible to require the least amount of battery, the least amount of motor, or move in the quickest of fashion. All of that can be easily simulated within Inspire. And again, all of this is driven from the CAD models you're already developing for your robots. We just bring them directly into Inspire, have it automatically define the behavior between the different parts, put motors on, stage them, and within a few minutes, be able to simulate and accurately simulate motion. So those are the three main things that we do with Inspire. It has other capabilities to it, but the main three that we talk about are structural analysis to make sure your parts are strong enough, optimization to make sure your parts are as light as possible, and motion to simulate dynamic systems, and then to couple it with analysis and optimization to make sure that we are developing dynamic parts that meet our requirements. And again, this was not training, but more so just an introduction to the art of possible within the software. If you want to get the software or want to be trained on it, this website right here, web.altair.com/firstrobotics, which is also the exact same link that's in the kit of parts. This is Altair's website that is dedicated 100% strictly to First Robotics. Everything on here was put on here with First Robotics in mind. From the top where we go to the free software to a video that was debuted at one of the competitions that we hosted that goes through and just kind of gives you an overview of Altair's involvement and Inspire and the things that we can do with it. To a student, Colin Dagg from the HOT team, and this was his presentation at one of our webinars that discusses his success with it, to our interview with Dean Kamen, which was, if you listen to Dean Kamen, he was Dean Kamen, and it was a very exciting and energetic interview. To getting the softwares, and we've got two of them that we mainly talk about. I'll talk about AI Studio in a minute, but Inspire, AI Studio, and then some others that are available. We've got webinar recordings, so you can learn from that. These are fully independent modules. In fact, everything that I brought up, aside from that solar car example, was from these. In that, in those, you will get an original file that you would start with, instructions as to how to go through and get to the end, all the steps that you need to take to set up that particular exercise. We've got a video where you got to listen to me, but I walk you through the process of setting that up. So if you'd rather watch a video on it, and then the final model, so you can compare it to what you've done. Each one of these modules walks you through that. So this is how you can learn the software. We got 6 modules for Inspire and 2 of them for AI Studio, which we'll talk about in a bit. And then if you want access to more of our software than Inspire or AI Studio, we've got a student edition that you can get. Access to webinars that we've had, more materials that we've got from webinars or training. When we open up the applications again, and I know that's coming up, I think it's going to be in the August timeframe, September timeframe. We will be offering grants to, there it is, September 1st, 2024. We're going to open it back up. We are providing financial grants to teams to support them, and you can apply for it there. And then we have a community within Altair on our community hub, where you can join the group and see other teams that are using it, ask questions, consult with the experts here at Altair. All of that is included on this web page and is really the best place that you can go to learn the software, get the software, and get help with the software. Finally, just some examples of teams that have used Inspire. I talked briefly about the HOT team. Their challenge was to strengthen a key robot part. They ran an analysis that showed in 2 different loading scenarios, 2 different hotspots, and you'll note that it broke exactly where it said here and exactly where it said there. And because they knew it was going to break, because the software told them the part that they had already designed was going to break, they were able to use the optimization tool to come up with a new design that went on the part and did not break for the entire rest of the season. And actually, the work they did on this was quoted by the judges at a competition that won them the Engineering Inspiration Award. And you can see some pictures of the part on the robot. Bearcat was looking for a stiffening member. They had a big plate, and they wanted to make sure that they placed material in the exact configuration that would make the part as stiff as possible, but utilize the least amount of weight. And so Inspire gave them this design, which they then translated into this. This was done with that manufacturing constraint, the extrusion constraint we talked about, to make sure that they could, this is metal, so I don't know whether it was laser or water jet cut, or even possibly just cut with a saw. But they utilized that, and here's the part on their robot, and that worked for them through the entire season. The Techno Dogs out of Michigan here optimized a gear, big heavy gear, and they ended up with a nice organic design that allowed the gear to raise and lower their arm, but utilize the least amount of material possible and the lightest weight possible. So all of the energy from the motor was going towards lifting the arm and not spinning that gear. The Goon Squad validated a new tube that they were looking to do. This was I can't remember, Max Spline. Their original spline part here was experiencing very high stress and was actually bending. They wanted to know whether the Max Spline was going to work better for them, but they didn't want to invest in them and test them out. So they tested them out virtually. The software told them it was going to work perfectly. It was going to lower the stress drastically. So they spent the money and bought them, and they worked perfect on their robot for the rest of the season. These are examples of teams that have actually utilized the software and had it work for them. One last thing that I want to talk about, and I know we were kind of talking about CAD and analysis here, but just to introduce you to one other option that you have with our software, it's a data analytics tool, a data mining tool called AI Studio. It was formerly known as Rapid Miner. It's a tool that can be used to help you make decisions. We've had teams that had great success with it, analyzing the past success, behavior, failures of other robots that have helped them pick alliance partners that complemented, that had a strength where their weakness was, or complemented their strengths. It's the use of data analysis, cleaning up scouting information, pulling information off Blue Alliance, and allowing you to make intelligent decisions. AI Studio is a fantastic tool for data mining and allows you to visualize data in a way that we normally couldn't. Data to us is just a bunch of numbers, and this allows us to see trends, to see behavior, to understand how to utilize that data to make intelligent decisions. From alliance choices, we had a team that used to determine where on the field excuse me, they should shoot their notes from. It analyzed all the information about where they had the best success for shooting notes and told them exactly where to go on the field to get the best opportunity to score points off the notes. All sorts of different opportunities for data analysis. And yes, I know that's not the CADs, but just wanted to make sure you're aware that other software was out there. Finally, Altair is looking to partner with teams. We want to make sure that we're not just putting ourselves in the kit of parts saying, hey, you can use the software, go figure it out on your own. We're providing you the material you need, but then we'll follow up with you and work with you personally if necessary. We have the team here in the US. We actually have a couple of offices in Canada, one in Toronto and one in Montreal, that have individuals that can work with teams. Hopefully, we're going to work with them to get to events eventually, and can work with you directly. And then, of course, we can also do things virtually with webinar for training sessions, for doing anything to help you out, to make sure you're not just getting the software and then being left. We're all in on this, and we're here to help you. And that's pretty much everything that I wanted to say. And actually even managed to do it in a little less time than I thought I would. So what I'd like to do is open it up for any questions that anybody has. If you want me to show you or demonstrate something, I'd be happy to do so. Uh, but otherwise, answer any questions that anyone has about anything that I've covered.
Yeah, I guess if
Yeah,
no one
you're
else
always
has
good for a
questions.
question.
Yeah, yeah. Well, honestly, my a few months ago, my manager at work, I'm on co-op at an engineering firm here in Markham. He was talking about Altair. He was like, you should try it for your robotics team because it's a better way to do topology optimization. Because the current way we do it is just like, okay, where are all the holes? Okay, put a border around the holes and connect them with
Yep,
kind of arbitrary webs. But he was like,
yep,
there's a better way. You should ask Altair to
absolutely.
sponsor. And well, I see you already do, so that's great. But yeah, basically, I'm very interested in the motor. I guess simulating motors, the motion analysis. So I was wondering if you could go through the process of taking, say, a CAD file, say a SolidWorks assembly, and setting up a motor, because I'd also be
Sure.
interested in, let's say we have the model of the motor already in there. Are you using that, or are you adding kind of a dummy motor onto it to simulate the motion?
Yeah, so the motor is a mathematical assembly. It is not,
Mm,
you're seeing a physical representation here, but that's just a graphical representation. What we do with the motor, so if I want to put a motor onto this, so say well, let me delete this one right here. Um, right now, if I run an analysis on this, so let me run an analysis, what you're going to see is it should only take about 30 seconds here. So let me do this. You'll see that just begins swinging. So I've defined a joint between these two, and it's just a hinge joint, which allows it to swing. So the inertia of it, the gravity is pulling down on this, and it's causing that to swing and swing back and forth. But obviously, I want to define some sort of behavior between this. So the first thing I do is I go through and I define all those joints. The joint here, you see it's defined as what we call a hinge joint. A hinge joint only allows revolution. It doesn't allow anything. So all it can do is this one geometry in here can spin within this other geometry, and that's why you get that behavior. We have other more complex joints, but in this case, it's a hinge joint. Then I come here and I say, okay, I want to put a motor on this, and I'm going to click on that. Oops, what did I? Oh, I think I clicked something behind it. So let me delete that. I come back here to motors. There we go. And I double click on that. And what it does is it attaches a motor to that rod right there. And I can create a motor that's attached between two bodies. Or if I just double click on one body, it essentially takes that motor and attaches it to that, and as if it's grounded on the other end. It still can move, but it will keep it in the same orientation against that part that I assembled it to. And then from there, I need to determine what is the driving force behind this motor. And I have the ability to create a speed, which is what it has right now. So this is in terms of RPM, an angle, an acceleration, or a torque motor. So one of these things, you can pick one, and that's going to be the driving force behind it. If I set this as speed, what's going to happen is it's going to ramp up to 60 RPM. And for as long as I have that motor active, once it ramps up in about a second to 60 RPM, it's going to continue spinning at 60 RPM. If I put it as a torque motor, so if I select torque, I'm going to put a torque in here. And if I put something absolutely astronomically small in there, so say, 0.01 inch pounds force. Oh, it doesn't like, oh, there we go. That was too small. It didn't like that. But I put a small number in there. It will try. It will put that much torque on there. But if that torque is not enough to cause this to spin, it won't. So it's going to be an actual behavior of that motor.
mhm.
But what I did in the example is I defined these as angle motors. So I'm going to say this is going to revolve, we'll say, I don't know what it was to begin with, so we'll say 90 degrees. And then I can come over here and look, and I see that it's going to start at 0, and half a second later, it's going to be at 90 degrees. Well, that's a little bit too quickly. So I'll say I'll give it a second to rotate 90 degrees. And it's going to rotate in this direction here. So then I can come and analyze it. And you'll see in 1 second that, oh, helps if I animate it, that rotates 90 degrees.
Yeah, that makes sense.
And then, what I did with the rest of these is, if I come and take a look at this motor right here, so highlight that motor, you see this motor actually has a different function. It's called a step dwell step. So step, it will go 120 degrees. It will wait a second. So it will start at time 1. It will take 2 seconds to go 120 degrees. Then it's going to pause at 120 degrees for 3 seconds, and then turn back in the opposite direction 120 degrees over the course of a second. So I can create, that's how I create that behavior of the arm, where it moves in one direction, then the next motor goes, and then the head turns. And so I can stage all these. And because I set them as angles, it doesn't matter how much torque it takes to do that job, it will do it, which allows me to then query this and find out what the torque requirement was. And so I see this is going to take 100 inch-pounds of force here. So if I took and I established this motor to be a torque-driven motor and only put 50 inch-pounds of force on there, it would accomplish this portion, but it wouldn't be able to do that. So you wouldn't see it move all the way, and you wouldn't see it spin all that way. It would do whatever it could.
So this can basically tell you the maximum amount of torque you need on
Yep.
the okay.
Yeah. Or if I know I have a 50 inch-pounds force motor, then I would put 50 on there, and it would tell me that the motor that I have can't do what I want it to, and it will show me exactly how it will behave. So these are mathematical representations of motors. They're not physical. There's no, brushes or electrical behavior inside of it. It's strictly a mathematical formula that says do this. And I can even go crazy with this, and I can look at, what did it? Oh, is it generating it? I can see there it is. This is the graph behavior of it. And I can manipulate this, or I could even import my own graph. So I know there's nothing from 1, and then the course of about a second, it's going to ramp up to 120, then it's going to stay there. I can bring in my own graph. Yeah, and do whatever I want it to do. And it does it smoothly to guarantee that you get a nice smooth motion.
Yeah. I guess one more question might be a bit more advanced for this call, but I guess I'd be interested to know, could you enter all the parameters of the motor? Say I have the kV of the motor and the internal resistance of the motor for a DC motor. Would I be able? No.
No, we can't go that in depth. It's a motion function. It's not actually taking into account the internals of the motor.
Okay.
So at least at this point in time. So
right.
Yep.
Okay. Yeah, sounds good.
So excellent. What and do you mind if I ask what team are you with?
7902. We're a Markham-based community team, so we have students from many different schools.
Oh, that's cool. Cool. Excellent. Where is Markham located?
Just north of Toronto.
Oh, okay.
We're the city just north of the Scarborough, North York area.
Ah, okay. Excellent. Cool. Yeah, I apologize on my familiarity with some of the. And I know where Toronto is. I know where Montreal is because I've been to both. And living in Detroit, I know exactly where Ontario is. So, but yeah, so excellent, good. And we've got the office in Toronto, so we can absolutely talk to you. If you want to work with people, we can see about getting them out there and working directly with you. So.
Oh yeah, definitely.
Excellent. Well, we got 5 more minutes. If there's no question, Musam, I see your hand up there. So.
Yeah. Hello, Erik.
Hello.
So, I'm very interesting. I have a very basic question. Like, can you define the material here, like aluminum, steel, because both have different weights and strength, right? Is it basic and define
let me apologize. The connection's a little echoey, so it was kind of hard to hear what you just said. I'm going to put my other earbud in and see if I can hear. But if you could repeat that, I'd appreciate it. It was just it was like a little echoey. So.
Okay. Do you hear me? Is it
Yeah,
okay now?
I can hear you.
Okay.
Yeah, it's just there's a little bit of an echo to it, but yeah, please repeat what you said, and I'll see if I can answer you.
Yeah, so it's a very basic question. Like, can you define the material here, like aluminum or steel, because both have different weight and strength, right?
Yes. Yeah, material. Absolutely. Okay, I heard you that time. I apologize. It was, yeah, it was tough to hear that. So so the material. If I come here and I right click on here, you'll see all of these materials from steel, AS 304, all these steels, these aluminum, titaniums, all the way down through plastic, nylon, and ABS. These are in the software. They come with the software. But if you've got a definition for a material that isn't in this, so the hot team, when they did their analysis on this, they defined a PA2. So these are actual material properties that came from the material manufacturer. I can add a material to this and put in my properties for it, and it will accurately calculate that. So you see this is PA2, and I can see that this is 0.242 pounds. If I change this to steel, for instance, it's going to accurately calculate the mass. And if I then included it in a motion analysis, the inertia of this, because of the change of mass, would be represented in the motion analysis. So it will very accurately represent all of the behaviors of the material. When I define material, you see I've got a mass density here, so it will calculate it. And I apologize, but I never mentioned this before. I've been in an inch pounds force, but we actually can change our units to whatever combination you want. So I'm in terms of inches, pounds, force, and seconds. Pounds, force, and seconds. I could go to millimeters, kilograms, newton seconds, millimeters, metric tons, newton seconds. I can do centimeters, grams, dynes, and however you want to define your units. You can switch it at any time. It will alter any material definition to be the new units, but maintain the same properties and report it back. So if I change to, now I'm in terms of kilograms, and all of my material is updated. So yes, we get a very accurate representation of the material in the library, or we can add our own. Hopefully that addressed your question.
Yes, yeah, thank you. I have one more question.
Yeah.
Like, like Arjun was mentioning, right? Uh, Regarding the motor, how will you know which motor to use? Like, what will you look for it? The torque or RPM, or what will you look
Excellent.
for
Yeah,
a motor?
excellent question. So it really depends on what you're, and I suspect in the vast majority of your cases, if you're moving an arm, you would define it as an angle motor, because you're going to know exactly the angle you want it to move to. But if you're defining it as if you're defining the motors that are driving your driving wheels, you probably would define them as the speed, so the revolutions per minute, to represent that. I would only use torque if I have a motor that I know the torque rating on it, and I want to see if it's going to work or how it's going to behave. I much prefer to do an angle or an RPM, and then click on that motor. Oops, let me get into the results here. Click on that motor and have it tell me what the torque requirements are, so I know I can size my motor appropriately.
For a shooter, what will you look for?
So for a shooter, if you're talking about the shooter, then you're more than likely if you're talking about the spinning the friction part that's going to grab the note and shoot it. Obviously, I'm talking last season. We don't know what next season is going to bring, but the wheel that's going to spin it, I would put the motor on there, and I would define whatever the RPMs are that are on there, spin it up to speed, and then I could measure the torque requirement for it based upon the size of the spinning disc that you're going to put on there. I could use that to determine the torque that's going to be on the rest of the assembly. But if I'm aiming that shooter, if I'm lifting it from horizontal and I'm aiming it and I'm pushing it up to say 30 degrees or 45 degrees, Then I'm going to use a motor where I do an angle driven motor, and I'm going to say spin or rotate this many degrees in this many seconds. And then if I needed to know the torque, I'd just click on it and it would tell me the torque requirement.
Thank you. That is what went wrong with our last project.
Oh,
The
is it?
shutter could
Okay.
not, could not
Gotcha.
lift it enough to shoot it.
Yeah, and this will
Thank
tell
you.
you, assuming you've modeled, you've got your CAD model and you assign the materials, this will tell you the exact torque requirement to lift your arm, and you can size your motor accordingly. So that's great.
Thank you.
You bet. Okay, well, it looks like we've hit the end here. I appreciate your time from everyone. Your questions, fantastic. Glad I could address it. Go to that website. It's in fact, what I'll do is let me copy the website name here, and I can put. I assume we've got a chat with this. I'll put it into there's the chat. I'll put it into here. So that's the website. Take a look at it. Get the software. If you have questions, feel free to contact me. We ultimately move all questions, hopefully, to the community. But this is my email address. If you have immediate questions or you want to talk about the webinar, don't hesitate to drop me a line, drop me an email. We can talk. We can see about getting you in touch with some of our Canadian colleagues, or we can help you. We just want to help you prepare yourself for the next season and build the best robot possible. So thank you all for your time. I really appreciate it.
Thank you very much again, Erik. Most appreciated. And what an amazing opportunity to build community here in Ontario and in Michigan and across the whole region. And what an amazing software as well. So it was a really appreciated presentation. And I'm sure the teams will be able to consider using the Altair software packages for their robot design. So with that, great to see everyone this evening and hope to see you all very soon.
Thank you so much for the opportunity. Take care.